Welcome everybody to this workshop where we're going to be examining some computational tools that we can use to ensure that our research workflows are open and fully reproducible. So we're going to be looking at a tool called Docker, which you'll be downloading to your computers, and a web resource called Docker Hub, which you'll be able to access from your computers. So very much in the context of research being open and reproducible, we kind of already know a number of things. We know that we need to make sure that our data are available to others. From a reproducibility point of view, of course, nobody can ever reproduce a research article that we've generated if we don't give them the data that we used in our analysis. Similarly, we also need to make sure that we share and make open our analysis code. So again, other people can run the analysis that we ran on our data and to make sure they find the same results that we did. So we already know that data sharing and code sharing are both important. But we also need to consider this third one down here, sharing of our computational environment. So why do we need to do this? Why is it important? And how do we go about doing it in the first place? So why do we need to reproduce the computational environment? So why do we need to share the computational environment that we had on our machines when we ran our analysis? Why do we need to share that with others? Well, a couple of very salient examples. One really focused on the fact that analysis code can break often in two ways. So what this means is that a script that you might have written using a particular version of R or a particular version of R packages, works fine as long as you're using the same version of R and the same version of the R packages that you used when you ran the analysis initially. But what can happen very often is that R will be updated, packages will be updated, and suddenly code that used to work now doesn't work. So one of the most recent cases that sort of affected the work that I do is that the ls means function, which I used to use to run pairwise comparisons, became renamed as em means. So old scripts that I'd written in R that I would run with a slightly updated version of R, slightly updated version of packages that included the ls means function now simply wouldn't run. And this, obviously causes a problem because it means your script doesn't run anymore. And unless you've got a bit of experience with R, this can be really confusing and can really throw you because you might think, well, the script used to work. Why is it not working now? So it's because of this change in one of the packages. So that's kind of an extreme case of a script that used to work, now not working at all. But there are other cases too, which are maybe a little more minor, but they still cause issues. So one of the cases is in terms of a package being updated, where the code still works, but actually now produces a slightly different result from the one it produced originally, or actually throws a warning where previously it didn't throw a warning. And again, in the context of the sort of packages that I use, when LME4 was updated once, it actually started making explicit warnings to do with convergence errors and singular fit errors, suggesting you're trying to estimate more parameters in your model than you're capable of doing. These kind of have always been there, but they were suddenly made explicit in version 1.1-20. And that caused a little bit of confusion when I was teaching the session, because suddenly the students were finding errors coming up when they built their mixed models that hadn't come up when I demonstrated those models to them. And that's all because of a difference between the versions of LME4. So that's kind of a focus on differences in packages, but there have also been differences in the way that R itself actually works. So what was discovered in R 3.6 was that the previous versions of the sample function actually had a slight problem with them. So the sample function was effectively rewritten in R 3.6. So if you're doing random sampling from a distribution, even when you were setting the seed to be the same as you had done previously, what you were getting in R 3.6 wasn't necessarily the same as what you were getting in previous versions of R. And in the context of random sampling, maybe for data simulation you were doing, this actually got really confusing because suddenly this random sample that you were generating, even though you were determining how to calculate it using or how to estimate it using set seed, was actually giving you different results from previous. And that was a problem. And then when R moved to R 4.0, one of the default parameters when associated with reading in data was actually changed from false to true. And this basically meant that some of the code that you might have written to read in your data that used to work perfectly previously now needed an extra line of code or an extra sort of explicit parameter being set in order to reproduce the same result that you had previously. So these are kind of issues then with R. So really what you need to be able to do to ensure full computational reproducibility is capture both the versions of the packages that you use in your analysis, but also the version of R itself. Without doing either of these things, you can't guarantee that you're engaged in generating fully reproducible research. Here's a great graphic from a wonderful paper by Roger Peng from a few years ago. You might recognize the name Roger Peng. Roger's one of the hosts of the fantastic data science podcast, Not So Standard Deviations. So he came up with this reproducibility spectrum where at one end we've got things that aren't reproducible, where you simply publish a paper, you don't provide any data, you don't provide any analysis code, so that's not reproducible at all. Provide your code and data, that's getting better. But actually what you really want to be doing is providing your code and data linked and executable in a computational environment. So you want to be providing your computational environment as well. And once you get up to here, you're basically producing research that is fully open, fully transparent, fully reproducible. So you can kind of think to yourself, well, hold on, Andrew, how on earth do we kind of share our computer with other people? We can't post it out to people. So what do? How do we capture our computational environments? And essentially, how do you share a copy of your computer with others? So we can do that using a fantastic tool called Docker. Docker is used widely in industry, maybe a little less so in academia at the moment, but it's a wonderful tool used by not only software developers, but also by data scientists. And Docker provides a way in which you can kind of package together your data, your code, your computational environment, which you can then share with others. So what you're effectively doing is creating something known as a Docker container that contains your data and your code, all the dependencies that then you can share with others. So when somebody else runs your Docker container, it's as if they're running your analysis on a computer that has the same configuration as your own one at the time at which you built the container. So it's a way of sharing everything with other people, including, importantly, sharing with your future selves. I've had many cases in my research career where I've tried to analyze data from a few years previously and I haven't been able to reproduce the same results because I've maybe updated a package in R, something else has changed. So you can create these Docker containers that are for other people to use. They can be linked to a journal article that you've published. They can be linked to your thesis that you've published, but also they can allow you to revisit your analysis at some point in the future in a really nice and easy manner. So Docker is an absolutely fantastic tool. It's absolutely huge. It's only been around since 2013, but it's really become the go-to standard for sharing computational environments and these kind of analysis scripts in the context of data science. You can click on this Medium article at the bottom here, which is a good introduction to Docker. So with Docker, as I said, we're building this container that contains our data, code, and computational environment, and then we can share that container with others. If you're doing an analysis in R, maybe using generalized mixed models, or you're building ordinal models, or some other model that requires a lot of computational power, you can actually build a Docker container on your laptop and then run it on a much more powerful computer that will do the analysis a lot more quickly. So you can actually share the container, not just with others, but you can use it yourself on a different computer that's maybe going to do your analysis more quickly. So an instance of a Docker image is called a container, and you can actually have many containers running from the same image. So you could create a Docker image and have like 30 other people working on it simultaneously. So this is all very much in the abstract at the moment. You're probably thinking to yourself, well, Andrew, you've talked about computational environments, this thing called Docker, images, containers. What does it actually mean in real terms? So what we're going to focus on in the rest of the workshop, I'm going to take you through how you run Docker both on Windows and on Mac. You're going to be building your own Docker containers. You can kind of see how they work. You're going to be running a Docker container that I've written. You're going to modify it. I'm also going to show you how you can build a Docker container that allows you then also to interact with things that are on your own laptop. If you remember from a previous session, we looked at a tool called Binder. So Binder is actually Docker under the hood. So Binder is a way to use Docker without getting into all the sort of nuts and bolts that we're going to be looking at today. But I'm sure you remember one of the pitfalls with Binder is that you can't change the analysis and then save it. You also can't access anything on your laptop from within the Binder itself. So what we're going to be doing today is kind of going beyond Binder to really look at what's going on under the hood in the terms of Docker and building these Docker containers that we can, where we can modify our script, where we can save things, where we can access things on our own computers. In many organizations, one way that they ensure that everybody is working with the same version of R or Python and the same version of the packages is basically build a Docker container that contains a particular version of the software that everybody on a research team is using. And that ensures that everybody's kind of using the same configuration. So it's a great tool if you're working in a large research group, if you're working on a research team in industry, to make sure that everybody's working with the same configuration of software. So the instructions for installing Docker on a Mac and a Windows PC are both very clear, hopefully very straightforward. I'm not going to demonstrate how you actually do this because I think the instructions kind of make it. Well, I couldn't make it any clearer than the instructions make it. So if you're on a Mac, wander off over up to this location and download and install Docker and then fire up Docker Desktop. I think it might actually start automatically once you've installed Docker. And then on a Windows machine, wander along to this link here and do the same thing in terms of downloading, installing Docker and running Docker Desktop. So I think in both cases, once you've got Docker downloaded and installed, you have to restart your computers. So once you restart your computers, make sure that Docker is actually running before moving on. So it could be a matter of just clicking on the Docker Desktop icon or going into the program files and double-clicking Docker Desktop there. So make sure Docker's running before moving on. And in the next couple of videos, I'm going to focus on how to get Docker running and how you build images and run containers on a Windows machine and also on a Mac machine. They're very similar instructions, but there's one or two minor differences. So I thought I would do separate videos depending on whether you're a Windows person or a Mac person. But hopefully once you kind of see Docker up and running, once you're playing around with it, you'll kind of be as amazed as I was when I first started getting Docker working, because it's a fantastic tool for sharing your research workflow and for doing fully open and reproducible research.